Okay, let's go ahead and finish up our lecture on the introduction to integration. And we're going to start with this lemma. This lemma is basically saying um, if you have two partitions and Q is finer than P, then these relationships hold. And let me just take a moment and show what it means to say that the lower sum with respect to P is less than or equal to the lower sum with respect to Q. So over here I've drawn some pictures and I have the same function f, right? It's not strictly increasing. And I have two partitions. So I have P and Q. Q is finer than P. So notice all of the points in P are also in Q, right? But Q contains two more points than P. So when I go to compute the lower sum of f with respect to P, I'm looking on each subinterval. I'm figuring out the infimum, and then I'm computing the area of the rectangle that has the height of the infimum and the width of that subinterval. And I do that for each interval, each subinterval in my partition, or created by my partition. And that gives me that, so the area of these blue rectangles gives me the lower sum with respect to P. Now, when I go to compute the lower sum with respect to Q, notice that for the subintervals that are the same, I'll have the same contribution of area, right? However, for the subintervals that have been split or divided, I'll have a different contribution of area. Because if I'm looking at this interval, now I need the infimum over this interval. It looks like the infimum is going to be this right here, right? So I have this rectangle plus, now I look over here at this other interval, and the infimum seems to be here. So what was before all of this area in blue, which is very low, now turns into the low part and then plus this better estimate. So remember, your lower sums and your upper sums are trying to approximate the area under the curve, right? Assuming that, of course, the function is above the x-axis. The graph of the function is above the x-axis. So your lower sums are going to be underestimates and your upper sums are going to be overestimates. A better lower sum is a sum that is closer to that area. So it's a sum that is greater, right? So by having the finer partition, I am able to better approximate my function, and my lower sum ends up being larger, okay? So that's kind of a geometric intuition behind the inequalities. Let's go ahead and prove it and walk through the proof. Again, the assumption is that P is a subset of Q, so Q is finer. And let's just look at this first inequality. So we're trying to show, is the lower sum of f with respect to P going to be less than or equal to the lower sum of f with respect to Q? And in order to answer this, let us reduce to the case where we're just considering one interval, because you can even see from the example that we have here, some of the intervals will be the same, but if we prove, if we prove that taking just an interval AB and splitting it up into two subintervals results in the area of the rectangles increasing, then we could then that justifies it being true for the total upper and the total lower sums, right? Because a lower sum is nothing but the sum of those rectangles. Okay, so let's just say, without loss of generality, our partition P is just going to be AB, and our partition Q is going to be A some point X 1, and B. So our lower sum of F with respect to P is going to be I want the infimum of F on AB times the length of that interval, so B minus A. And then on the other hand, my lower sum of F with respect to Q is going to be the infimum of F first on A to X1 times the length of that subinterval, which will be X1 minus A. And then I add to that the height, which is going to be the infimum of F on the interval X1 to B, okay, times B minus X1, okay? Now, the key to seeing this is to notice that B minus A really is equal to B minus X1 plus X1 minus A, right? So I can rewrite this as, I can rewrite my sum as my infimum of F over AB times B minus X1 plus, well, let me actually rewrite it down here. So F of P is going to be my infimum of F over AB times B minus X1 plus my infimum of F over AB times X1 minus A. So all I've done is take my B minus A, write it as this plus that. This is being multiplied by these two things, so I just distribute this times this plus this times that, and that's how I get this plus this, okay? Now, I'm trying to compare the partition with respect to P to the lower sum of F with respect to Q. Everything, oh, I should have rewritten it. Let me switch this around. Okay, so that it's really easy to see exactly what we're comparing. Okay, so now I'm going to be able to have my result follow from the fact that the infimum, so the set of f of x such that x is in between a and x1, that set is contained in, it's a subset of the set of f of x such that x is in between a and b, right? So any number that is a lower bound of this set is always going to be also a lower bound of this set, right? So the biggest lower bound, so let me see here. So let's kind of draw a picture here. So suppose you have some set here, S, and S is inside a bigger set, T. Okay, now the infimum for S is going to be bigger than or equal to the infimum for T, right? Because every lower bound for T is also a lower bound for S. So the infimum of T is a lower bound for S. So the infimum of T has to be less than or equal to the infimum of S, because the infimum of S is the biggest lower bound of S, right? So I know that we did this proof back in the beginning of the semester, but if S is a subset of T and the infimum of both exists, then the infimum of T will be less than or equal to the infimum of S. So here we have subsets. So of course the infimum of the larger set is going to be less than or equal to the infimum of the smaller set of the subset. This is precisely my M of F on AB. Okay, and then this right-hand side is my M of F on A to X1, right? So we've shown that this is going to be less than or equal to this, right? So since this is less than or equal to this, similar reasoning implies this is going to be less than or equal to that. So these quantities being multiplied by positive numbers will have their sum less than or equal to the sum over there, okay? So that is true. And just like we have that, so let's look at, or let me go in order. So we've proven number one. What about number two? That the infimum, or the sum, the lower sum is going to be always less than or equal to the upper sum. That is kind of, that's kind of straightforward. So the lower sum of f with respect to q is less than or equal to the upper sum of f with respect to q. That's pretty straightforward because for each subinterval, say xi to xi plus 1, the infimum of f of x such that x is in between xi and xi plus 1, the infimum of that set is going to be less than or equal to the supremum of it, right? This left-hand side is equal to little m of f at q, and the right-hand side is big M of f at q. So my lower sum is the sum of these little m's, the little m's of f over the interval times the length of the interval, right? And that's the sum of the big M's times the length of whatever. Let me go back and correct this because that's not q. That should be xi plus 1. And this should be xi plus 1. So I'm sorry my Apple Pencil is not doing the best job, but you can follow the reasoning to say that the lengths will be the same, but you're multiplying, the nth will be less than or equal to the sup. So each of the terms that you're adding up on the left-hand side will be less than each of the terms you're adding up on the right-hand side. So the total sum, which is that lower sum, is going to be less than or equal to the total sum on the right-hand side, and that's the upper sum. So that's number two. And then number three, the proof for number three, this inequality here, why is it the case that the upper sum over the finer partition is less than or equal to this one? The proof is going to be exactly the same or very similar to the proof for number one. The only thing is that for number three, use the fact that if S is a subset of T and S and T are bounded and non-empty, then what's true about the infimum of S versus the infimum of T? So we can just draw a sketch. So say here's T and here's S. The infimum of S is going to be less than or equal to, the supremum of S is going to be less than or equal to the supremum of T. So because of this, if Q is finer, when you're adding up the soups over those subintervals, that's going to be less than the soup over the bigger interval. Okay. So the reasoning that you use to explain the inequality number 1 is the same as the reasoning that you use for the inequality number 3. You just use the analogous fact about soups of subsets. Okay. All right, okay. So let's look at this other lemma. This says, suppose you have a bounded function. And again, we assume that our function is bounded so that these soups and ifs are guaranteed to exist. Okay? Because otherwise we might be talking about quantities that don't even exist, right? So everything that we do in integration is going to assume that our functions are bounded. And suppose we have P and Q are 2 partitions, but now P and Q aren't necessarily, P isn't necessarily finer than Q or coarser than Q, if that makes sense, right? So the claim is that basically any lower sum is going to be less than or equal to any upper sum. And the hint for the proof is to consider P union Q. So this is going to be a brand new partition. And the benefit of this partition is that it includes, or it is finer than both P and Q. All right. So what we said from before is, so if P, or if P union Q is finer than P, then that means that the lower sum of F with respect to P is less than or equal to the lower sum of F with respect to P union Q, right? By our lemma. And now the lower sum of F with respect to P union Q is certainly going to be less than or equal to the upper sum of F with respect to P union Q, right? And then that upper sum is a better estimate than the upper sum of F where you're just using Q. So this is since Q is a subset of P union Q, and we're going to apply inequality 3 from the lemma, from the previous lemma. And then here, we're just going to apply the second inequality from the previous lemma. And then here, this is because P union Q is finer than P. We can apply the first lemma. So this is really telling us, this is really telling us that any lower sum is less than or equal to any upper sum, okay? Now let's look at this theorem. This is a huge theorem. This theorem is saying that the lower integral is always less than or equal to the upper integral. Okay? Now remember that the lower integral, so let's say recall, and you all didn't know that Michael Jackson song that starts off, "Do you remember?" So I might include a link to that video. Okay, recall that the lower integral is the supremum of all the lower sums, right? And the upper integral is the infimum of all the upper sums. Yeah? Let's see, for some reason my pen is streaking, but... Okay, so if we are trying to show that the sup of the lowers is less than or equal to the nth of the uppers, one way we can do it is as follows. So I'm looking at our sketch here. In our sketch, copy. Let's add a page here. So our goal, let's put our goal, or hypothesis, we can do a formal proof. So hypothesis is that f is bounded, and the claim is that the lower Darboux integral is less than or equal to the upper Darboux integral. Okay, so for the proof, the first thing we're going to do is we're going to prove that any lower sum is a lower bound for the set of upper sums. So first, we show that any lower sum is a lower bound for the set of upper sums. So for each P, partition P, and for each partition Q, the lower sum of f with respect to P is less than or equal to the lower sum of f with respect to Q. But this is a direct consequence of the last lemma that we proved, right? So the last lemma said that any lower sum is less than any upper sum. So if we think about, so say this is the true integral, right? Assuming that the integral exists. All your lower sums are over here. They're underestimates. And all your upper sums are over here. They are overestimates, right? So any lower sum is a lower bound for the set of upper sums. That's what we're saying. And if we kind of keep with our little picture here, right? Any lower sum is a lower bound for the set of all the upper sums. That means the infimum of the upper sums has to be bigger than or equal to every single lower sum, right? So that means that the infimum of the upper sums is an upper bound for the set of lower sums. So the infimum of the upper sums has to be bigger than or equal to the supremum of the lower sums. Okay? So let's write that out. So this one is by the lemma. So we conclude that for each P, LFP is less than or equal to the infimum of the set of upper sums. This should be a U. So this means that this number here is bigger than or equal to all of these, right? So the infimum of the set of upper sums is an upper bound for the set of lower sums. right? So this number is an upper bound for this set. The sup of this set is the least upper bound. So the sup of this set of lower sums has to be less than or equal to that number there, which is the nth. But what is this sup? That is nothing but the lower integral. And what is the nth of the upper sums? That's nothing but the upper integral. So we've got that lower integral less than or equal to upper integral as desired. Right? So based on this, one strategy, a good strategy to use if you want to prove that f is Darboux integrable, prove that the upper integral is less than or equal to the lower integral. Because we have the theorem saying that the lower integral is always less than or equal to the upper integral, right? So if you prove that the upper integral is less than or equal to the lower integral, you'll prove equality. And that's what it means for a function to be Darboux integrable. Okay. So let's go over here. And I just want to mention, this is the last thing we'll talk about. This is the Cauchy criterion for integrability. So again, we're starting off with a function that is bounded. And remember, I was saying that as we're working through integration and everything that we're doing, keep track of where is the limit, right? How are limits involved in what we are doing? That's a question. This is kind of getting us close. We're talking about Cauchy criterion here, okay? So suppose you have a bounded function. Then f is integrable, right? If and only if, for each epsilon, there exists a partition of p such that the upper minus the lower is less than epsilon. So let me try to show you what this means. Now, suppose your function is integrable, right? And this is the integral of f. That means that your upper is equal to, I think I'm going to draw this out. Okay. If f is integrable, that's true if and only if your lower f is equal to your upper f, right? Which is really true if and only if your upper is less than or equal to your lower integral. Because we just proved the theorem that says that your lower is always less than or equal to your upper, okay? So now, imagine this is that integral of f. So this is equal to your upper, and this is equal to your lower. Now, your lower, this is supposed to be the sup of the lower sums. So anything above it, right? Anything above it must not be a sup. Must not be, so the sup is the, sorry. Let me switch that around. Okay. Anything below it must not be an upper bound, right? So L of f minus epsilon isn't an upper bound for the set of lower sums. Right. And then similarly, anything, since our upper integral is the infimum of the upper sums, anything bigger than it must not be a lower bound, right? So u of f plus epsilon isn't a lower bound of the set of upper sums. Okay, so the definition of soup, remember we gave like 2 or 3 different definitions of soup or characterizations of the supremum of a set and infimum of a set. One of those characterizations involved epsilon. That is what we're using for this proof right here. That's why we're concerned about the epsilon. So looking at this, we can rewrite this. So we're saying f is integrable if and only if for each epsilon there exists a partition. So for each epsilon greater than 0, there exists a partition P such that u of fp is less than L of fp plus epsilon. Right? And also, L of fp is bigger than u of fp minus epsilon. So if we look at our number line here, let me kind of move this out the way. So if we look at our number line, we're really saying that f is Riemann integrable if and only if for each epsilon there's a partition P such that u of fp, right, that upper sum, is less than L of fp plus epsilon. So L of fp plus epsilon kind of puts you above, L of fp plus epsilon puts you above some upper sum. And if you have an upper sum, then that upper sum minus epsilon is below some lower sum. So it's kind of like the upper sums and the lower sums are thoroughly mixed, if you will. So let's go ahead and let's jump into our proof here. Let's do our proof. Let me actually do a different page here. So for the proof, let's start off with hypothesis f is bounded. And f is Darboux integrable. And the claim is that for each epsilon greater than 0, there exists a partition P such that the difference between the upper and the lower partition is less than epsilon. Okay, so for our proof, we're going to say suppose or fix epsilon greater than 0. Then, I'm just looking at my sketch here. So f is Riemann integrable. So somewhere this is my lower integral is equal to my upper integral. Okay. Now, this lower integral is the soup of all of the lower sums. So that means that if I look at this lower integral plus, or if I look at this lower integral and I just look at that minus epsilon, So then the lower integral minus epsilon is not the is not an upper bound of the set of lower sums, because remember, the lower integral is it's the soup, so it's the smallest upper bound of all the lower sums. So any number that's smaller than that lower integral can't be an upper bound, because the lower integral is the soup. It's the smallest of the upper bounds. Okay. So since L of f minus epsilon is not an upper bound, this means there exists a partition P of our domain AB such that so here's our L of f. Here's L of f minus epsilon. This L of f minus epsilon is not an upper bound, so there must be some there's a lower sum that's bigger than L of f minus epsilon, right? Okay. So L of fp is going to be less than L of f, but bigger than L of f minus epsilon, okay? And similarly, for the same reasoning, now remember this L of f is also equal to U of f because because our function is integrable, so that upper integral is equal to the lower integral. And if this is the infimum of the upper sums, right? So this is supposed to be the greatest lower bound. So anything bigger is not a lower bound. So if I look, say over here, if I look here at U of f plus epsilon, I don't know what's wrong with my pen. If I look at U of f plus epsilon, there has to exist, say, a Q, partition Q, such that the upper sum of f with respect to Q is less than the upper sum of f plus epsilon, okay? It's going to be bigger than the upper sum of f, okay? So now let's look at the partition P union Q. So let P tilde equal P union Q. Then what must be true? Because so far, well, let's see here. My lower sum of, let's see here, if I have P union Q, then my lower sum of f with respect to P union Q is going to be bigger than or equal to just that lower sum with respect to P. And it'll be, the upper sum is going to be less than or equal to this one, which is that's my upper sum of f with respect to Q, right? So let's try to work this out. So by our lemma, our let's see here, the lower sum of F with respect to P union Q is going to be bigger than or equal to the lower sum of F with respect to P. It'll be less than or equal to the upper sum of F with respect to P union Q, and that is less than or equal to the upper sum of F just with Q. Now, let's see here. I'm looking at this, and from my picture, the difference between these two has to be, right, so let me use a different color. These two have to be closer to each other. So somewhere in here is my L of F P union Q, and somewhere in here is my U of F P union Q, right? So these two have to be closer than these two, and these two are closer than the difference between these two. And we know exactly how far these two are apart, because from here to here is epsilon, and from here to here is epsilon. So this whole distance is epsilon. There's 2 epsilon. So the distance between these two has to be less than or equal to 2 epsilon, right? So this is this left side is bigger than or equal to L of F minus epsilon. The right-hand side is less than or equal to U of F plus epsilon, right? So U of F let's see here. U of F with P union Q minus L of F P union Q has to be less than or equal to U of F plus epsilon minus L of F minus epsilon, right? And again, the idea is that these two have to be closer to each other than these two, right? And we know these two are exactly 2 epsilon. So my goal was to show that for any epsilon, I can find a partition such that the upper sum and the lower sum with respect to that partition are within epsilon units of each other. And what I've done is I've shown that there's a partition, this is going to be P union Q, such that the upper and the lower sums are within 2 epsilon of each other, right? So to get it so that for every epsilon there exists a P such that this is less than epsilon, I'm just going to go back, and instead of using epsilon here, I can just switch this to be epsilon over 2, right? And switch that to be epsilon over 2. Now this distance is epsilon over 2, epsilon over 2. My whole interval is epsilon. Right? And I found what I want, right? So I could go back and switch, and instead of having, because the P that I'm using here is really my P union Q. So P union Q satisfies the claim as desired. Okay, so basically what we're saying is if F is Darboux integrable, then we can find upper sums and lower sums that are within epsilon units of each other. Okay, so we can get those upper sums and those lower sums as close to each other as we want. Is it starting to sound like limit, right? You get how we're using limits? Okay, so we just have one more piece, which is to show the other side of this. So suppose now that, trying to show the other direction in our proof. So suppose now that f is Riemann integrable, and for any epsilon, we can find a partition such that the upper and the lower sums with respect to that partition are within epsilon units of each other. Well, now we're trying to prove that f is Darboux integrable, okay? So here's what we'll do. So let's start off and say that we're always going to have, my Apple Pencil, something's wrong here. So by hypothesis, for any epsilon greater than 0, now let's draw our little number line so we can kind of imagine what's going on here. And we're saying that for any epsilon greater than 0, we can find a partition where the upper sum with respect to that partition and the lower sum is, that difference is less than epsilon, okay? And we're saying that's true for every epsilon. Now remember, my upper, so there, let's put, there exists a P such that the upper sum minus the lower sum with respect to that partition is less than epsilon. So now my upper integral is the infimum of the set of all these upper sums, okay? So that means for each partition P, my upper integral is going to be less than or equal to that upper sum with respect to P. But now what is that upper sum, right? So say this is here. Maybe my upper integral is there, right? So maybe that's my upper integral. Okay, I can write my upper integral as the upper sum plus the difference between, I can write it as my lower sum plus the difference between my upper and my lower, right? So this would be, this would be this upper, right? So my upper integral is the lower plus essentially epsilon, right? So I'm looking here, and this is going to be less than or equal to the lower plus epsilon. But remember that the lower has to be less than or equal to my lower integral. Right? So if I have some lower sum plus epsilon, that's going to be less than or equal to L of f plus epsilon. Right? Now, all of this is true for any epsilon. So what we've shown is that for any epsilon, I can use the hypothesis to conclude that, let's write it down here. So for any epsilon greater than 0, we have that my upper integral is less than or equal to my lower integral plus epsilon. So this means upper integral has to be less than or equal to the lower integral. Because remember, a is less than or equal to b if and only if a is less than or equal to b plus epsilon for any positive epsilon, right? And so if I know that my upper integral is less than or equal to my lower integral, that implies that my upper and lower integrals will actually equal. So my function is integrable. Okay. All right, so we've done the proof. This now gives us a characterization of being Darboux integrable. And it's a characterization in terms of epsilon. So the reason why this is called a Cauchy criterion is because we're saying that your function is integrable if and only if the upper and the lower sums are arbitrarily close to each other. Right, so if you can always find a partition that's going to have your upper and lower sums to within epsilon of each other. Remember, your lower sum is your underestimate. Your upper sum is your overestimate. So we're saying your function is integrable if and only if you can get lower and upper estimates within epsilon for any epsilon. Sorry about that. Okay, so now on Monday, we'll introduce a different kind of integration. This is Riemann integration. This will again be a generalization of the integration that we learned in calculus, right? And so we will be introduced to the Riemann integral, and we'll learn that it is equivalent to being Darboux integrable. Okay? All right, and then the last kind of topic in this section of integration will be the fundamental theorem of calculus that combines integration and differentiation. Okay? All right, as usual, let me know if you have any questions.